So with that, I would like to introduce our first speaker, Mr. Aniruddha Nakhawa. Mr. Aniruddha Nakhawa is a leading structural engineer and project management consultant headquartered in India and a member of numerous ACI committees, ACI Committee 228, 396 and 546, and is an active member of the India chapter of ACI as well. Mr. Aniruddha Nakhawa has worked on numerous challenging projects. Just a few highlights: successfully designed 800 low to high rise structures, successfully audited 6,000 buildings in India, and successfully assisted in 250 plus structures in terms of repair and rehabilitation. So with that, I invite Mr. Nakhawa to make his presentation.
Okay. Thank you, Saurabh. Good evening, ladies and gentlemen. We all are aware, in fact, we learn from our failures. And failures make us think and think and think over again and again. There was a drastic collapse in 2013 in one of the suburbs in Mumbai metropolis named Thane, and the ongoing construction of G+8 building, a non-engineered structure, collapsed while construction, and almost 24 lives costed for that failure. Since then, I started counting those buildings. We surveyed from 2013 to 2019, and we made a cluster of these buildings to form 800. It was not deliberately done, but the total buildings accounted were 800 buildings, and this is the state of art assessment of 800 non-engineered and engineered buildings in Mumbai metropolis, Thane and Ulhasnagar. Why I have not specified Ulhasnagar and Thane? Because these are small suburbs, counties just besides Mumbai city. In last 2 decades, Mumbai city witnessed major collapses of RCC buildings. Mumbai also experiences at the same time heavy rainfall and saline climate. Scientific and statistical interpretation of structural health assessments of these 800 buildings in suburbs vis-a-vis Thane and Ulhasnagar cities, where frequent building collapses during monsoons has become very common. Yes, sorry for the interruption. We are struggling with technology here too. What I was telling is, advanced technology is a boon as a result of learning from failures. Failures have always guided us in making new innovations, technologies, and research. Such incidences and socio-economic issues have inspired the author, that is myself, to do such big data analysis. I am Aniruddha Nakhawa, structural engineer from Mumbai, presenting to you the state-of-art assessment of 800 non-engineered and engineered buildings in Mumbai for corrosion, damage, and residual life. As we know, Mumbai is experiencing heavy rainfalls, saline climate. There are many collapses happened in last couple of decades rather, through which the government and civic bodies are continuously improvising of the steps to take place and to be taken, so that in near future we avoid such collapses. And this research will be, I think, of use to many such planners in big cities as well as globally. This assessment took 6 years, and relationship with the respect to age and damage was monitored. Degree of corrosion and carbonation was related to the loss of section and load carrying capacities so that it helped the engineering community and the city planners to deal with these structures to improve their performance, make directives for their safety, stability, and safeguard life in these buildings, and take appropriate steps to rehabilitate and build sustainable future. NDT and NDE are corroborated with special visual condition assessment. A scientific and statistical interpretation of the data has been done with objective to estimate the residual life of these structures. Friends, we live in an urban century where more than 50% of the global population lives in urban areas. The United Nations estimates that by 2030, 5 out of 8 billion of the world's population will live in urban areas. Mumbai has a tropical climate, as you can see in the graph, adjoining graph, which shows precipitation, temperature, and the rainfall in the area. The rainy season falls in June to September for 4 months, known as monsoons in India. Mumbai also experiences extreme saline climate and almost 100% humidity during the rainy seasons, with the average of 68% of humidity throughout the year. Thane and Ulhasnagar cities near Mumbai form western side coastal part of India. You can see this Google Earth pictures. Extreme left is Mumbai, which is an 800-year-old city developing gradually, and it's now running to compete with the world. Thane is also the suburban 800-year-old city. Ulhasnagar is post-independent city, that is, its development started after 1947. The 800-year-old historic suburban Thane city with a population of 8.5 million is distributed over the area of 147 square kilometers. It is the 16th most populated city in India as per 2011 census. Evidently, it is the heavily populated city on the coast. You might be thinking why I am specifying these statistics. This is just to know. The table below will show you how many people live in such dilapidated buildings. According to civic records, nearly 20% of Thane city's population is residing in structurally unsafe buildings which have been declared as dilapidated structures by the authorities. Moreover, these buildings are unauthorized and occupied at the risk of fatalities, which may arise due to structural failures, earthquakes, and fire hazards. In last 2 decades, more than 162 fatalities and 120 injuries have been caused due to incidences related to such dilapidated buildings. When we took at the scene, a small city like Ulhasnagar is comparatively of recent origin. Around 10,000 buildings with almost 95% of these buildings constructed are non-engineered buildings. 864 buildings of these have been declared as dilapidated by the civic body. You can see in Thane city there are 2.6 million people living in 2,624 buildings, and in Ulhasnagar 0.6 million people living in 834 dilapidated buildings. As mentioned earlier, there is a large inventory of non-engineered and semi-engineered structures in and around Mumbai. These structures come for repairs, restoration, as well as collapses at regular intervals. These not only result into loss of property and invaluable life of ignorant, gullible occupants. The process happens year after year. This is an effort on large sample of 800 structures to assess the present engineering status with the help of non-destructive testing and evaluation. This data is considered as prerequisite to look at the model to enhance residual life of structures in India and world at large, which faces similar weather conditions and quality of construction and safeguard the valuable property and more precious life. Let's see what the methodology we adopted for the data was. A sample of 800 buildings. The sample type included low rise as well as high rise up to 9 story. These buildings were RCC framed as well as load bearing structures or combination of both. The year of construction of this sample was from 1900 to 2007. The period of inspection carried out for this 800 buildings was 2013 to 2019. Initially, structural health assessment behavior with respect to age and damages was monitored, including NDT and NDE. Representation of this data for 800 buildings on worksheet was done as below. This is a sample worksheet where you can see the job of location, name of the building, year of construction, age at the test date, type of structure, carbonation depth, US PV kilometers per second, and the half cell potentiometer for both the cities was included. We carried out a health assessment drive in order to ascertain the level of distresses, damages, arrive at appropriate conclusions, and derive recommendations. And conventional structural health assessment, which is referred as structural audit in India, was carried out by adopting sequential procedure like study architectural and structural drawings, design criteria and design calculations were considered. We prepared as-built drawings, visual inspection, non-destructive testing, partial destructive testing, push-over analysis, and then conclusions and recommendations. I am not going into detail of this because this paper has its own limit, this presentation has its limitation. Methodology adopted also further included that we categorize these buildings on the conclusions and recommendations arrived in each individual cases and categorized as per the civic authorities guidelines and codes in India. The categorizations of the buildings as per the assessment reports included C1, C2 and C3 categories. Namely, C1 is the structures to be raised down, C2 structures to be repaired, and C3 structures is unsatisfactory and maintenance required. So you can see there are total 98 buildings in C1 categories, in C2 categories 261, and in C3 258, totaling to 800 structures. The results of 800 buildings were plotted graphically for two different places, Thane and Ulhasnagar. The NDT and NDE data of all these buildings were analyzed to evaluate every individual case. The interpretations are presented in statistical form and results are plotted by segregating the buildings according to their age and day of testing. The sample of buildings was further clustered as per the age, the period in decades of construction. The results of individual structures become the part of data of decade it belongs. The NDT results are further plotted for parameters as below: age of building versus carbonation depth, age of building versus ultrasonic pulse velocity, age of buildings versus half cell potentiometer. At the outset, for the 800 buildings, more than 28,000 UPV readings, 12,000 plus half cell potential readings, and 12,000 plus carbonation depth readings were taken, and these were recorded and interpreted on site visually and analyzed graphically as well. As mentioned earlier, the groups you can see this period included for ease of calculation and understanding the time period calculated for year of construction and day of testing, where these periods include buildings existed below 1958 to 1969, 1969 to 1979 and so on till 2019. Similarly, for the other city it was done. The non-destructive testing results of the building existed in both cities are plotted for carbonation, corrosion, UPSV with respect to age of building at the time of NDT testing. These comparisons are plotted separately for each decade from 1959 to 2019. Further, for global interpretations, all these parameters are plotted independently for both cities over 60 years period. The factor of safety for individual members of typical buildings are calculated based on geometry of the building, visual inspection, damages and loss of section, NDT results, core testing, design load and the actual load. This is a typical worksheet for calculating factor of safety from pushover analysis and results. You can see we have a typical data has been put over column, beam and slab, concrete section, the design effective area, and the effective area as on the date of testing. Similarly, the reinforcement which was at the time of design, the effective reinforcement which is available after the corrosion, and the actual load in kilonewtons which is there on the building as on today on the section. The section capacity, design and the actual was worked out, and the factor of safety was worked out as per the Indian codes of standard codes of practice, that is IS 456 2010, which prevails in India and we have to follow that. They were tested in compression as well as flexure. The interpretations of these, we prepared more than 2400 graphs for each cases, that is 800 into each test. We had 3 tests, so 2400 graphs were prepared, and these graphs were compiled as per the decades also. For example, there were, for example, for 1960 to 1970 there are 10 buildings, so individually also the graphs were prepared, and a cluster of 10 for 10 buildings also the graphs were prepared, and for further global interpretations these graphs were extended to the global graphs. So you can here see here a sample graph of carbonation versus age versus carbonation, age on x-axis, carbonation on y-axis for the period 1979 to 1989, and the average lines were drawn, and these were interpolated and brought to the global graphical representation. Sorry. Similarly, you can see the graph for age versus USPV and age versus half cell potentiometer. And these are the graph for average on overall period for Thane city. The graphs which you see at the top are for one of the Thane city, and graph for Ulhasnagar city are the one at the bottom, and for all the 3 tests, and these were further combined together to form the final graph. In addition to above independent interpretation of NDT results, a combined analysis to study the effect of damage, corrosion, carbonation, environmental effects, type of exposure and use with respect to age of the buildings are presented in tabular as well as graphical form. This is the global graphical representation. In next slide I am showing you the tabular form of combined comparison of average carbonation, USPV and corrosion versus age of the cities. You can't see the cursor there, no? See, for both the cities, you can see the carbonation depth, the averages, USPV and half cell, and from these the averages are taken for all the decades for city 1, then for Ulhasnagar city, that is the city 2, the averages are taken for all the decades, and for both the cities the total averages have been taken. Let's come how the results were arrived and interpretation was done. Based on the above observations, it can be seen that in the Thane city, where the sample was 635 buildings, maximum carbonation is seen to be initiated from 22 years of age for buildings constructed in the period of 1989 to 2019. The rate of carbonation is estimated in the range of 1 to 1.25 millimeters per year for the buildings constructed before 1989, whereas it can be seen that it has increased to 1.5 to 2 millimeters per year for the buildings constructed in the period of 1989 to 2019. The average rate of carbonation for all buildings is estimated is 1.59 millimeters per year. The half cell potentials are in the range of minus 282 to minus 349 millivolts, are indicative of probability of corrosion varied from 50 to 90% in last 4 decades. The average USPV is recorded below 3 kilometers per second for all the buildings tested in the city number 1, that is Thane city. For the second city, that is the Ulhasnagar city, the maximum carbonation is seen to be initiated from 15 years of age for the buildings constructed in period of 1990 to 2019. The rate of carbonation is estimated to be 1.1 millimeter per year for buildings constructed before 1990, whereas it is seen to be increased to 1.8 millimeter per year for the buildings constructed in the period of 1990-2019. The average rate of carbonation for all buildings estimated in Ulhasnagar is 1.5 millimeters per year. The half cell potentials varied from minus 305 to minus 325 millivolts, which are indicative of probability of corrosion varied from 50 to 90% in last 4 decades. The average UPV recorded below 3 kilometers per second for all buildings tested. Friends, it can be seen that there is a loss of effective cross section of concrete as well as the rebar due to carbonation and corrosion. The pushover analysis showed substantial reduction in factor of safety of the structures in individual cases and age groups, that is as per the decades considered. The methodal conclusions. The methodology adopted to assess the level of damage and corrosion with respect to age of the structure from available scientific as well as statistical data in each individual case and groups. From overall observations, analysis and interpretation, in this case study of 800 buildings, where more than 90% of the buildings assessed are non-engineered buildings, it can be concluded that the buildings constructed before 22 years of age, that is before 1997 in Thane city, and before 15 years of age, before 2004 in Ulhasnagar city, have performed better than those constructed thereafter, because they are non-engineered. The building constructed thereafter in these cities were observed to show severe deterioration and damages due to precipitation, chloride action, non-engineering and bad construction practices, as a result of socio-economic reasons. Further structural additions and alterations have also resulted in failure of major structures in this region. Friends, the range of years where the design life appears to cease is where the residual life of the building begins. Though a critical task, but a well-versed expert can have his hands on it. It is apparent that the buildings with age 22 years and above in Thane city and with age of 15 and above in Ulhasnagar are strongly recommended for structural health assessments in detail, followed by appropriate strengthening measures. The above approach is a precursor to establish a model to enhance residual life of several non-engineered, semi-engineered structures, resulting into prevention of loss of property and life. I thank all the building users of 800 buildings for allowing me to do this research and do the testing of their buildings. I thank our local civic authorities, Thane Municipal Corporation and Ulhasnagar Municipal Corporation, Professor Dr. V.B. Deshmukh from VJTI Institute, Dr. S.K. Manjrekar of Sunanda Global, and Dr. Pedro Castro Borges from Alconpat, India chapter of ACI, Saurabh Manjrekar and Ishita, and I thank the all ACI community at large. Thank you so much.